So today is a bit on lifting machines, and all a lifting machine is something that's designed to lift something. So it's designed to raise or lift a load by a smaller effort. That's the idea of a machine, to make things a bit easier for us. So things like pulleys, cranes, car screw jacks or car jacks, block and tackle, they're all lifting machines, and they enable us to lift a load, a weight or a mass, by a smaller effort. That's why we use pulleys and we use cranes. If you've got a flat tire, it's quite hard to lift your car up, so we use a screw jack, and the screw jack enables us to lift the car, which is the load, by a smaller effort. And the law of the machines and the lifting machines enables us to do that. So for example, here's our pulley system. For example, here's my load. FL just means load, and E means effort. So this is you pulling on it. And the way we do pulleys, depending on how the system is designed, the effort that we use or we put in lifts the load. Without the pulley, we probably wouldn't be able to lift that load. But the law of the machines and the mechanical advantage that the machine produces enables us to lift the load. That's the reason why we use things like car jacks, lifts. So for example, the pulley above could enable us to lift a 500 Newton load. So this here could be a 500 Newton load. Normally we wouldn't be able to lift that perhaps. So the effort that we produce would be a lot less than 500, it could be 50. So the way we would set up the pulleys or this lifting machine, that we could put in an effort of 50 newtons and we could lift 10 times as much. That's the mechanical advantage. That's the reason why we use machines. So FL just means the force of the load, and FE just means the force of the effort. So in this case here, let's see if I can write. In this case, this load would be 500, so FL would be 500, and the FE would be 50 newtons, obviously. So the mechanical advantage, first formula, mechanical advantage is force of the load over the force of the effort. MA stands for mechanical advantage. There's no unit, just FL over FE. So for example, in this one here, the mechanical advantage of that machine would be FL, which is 500, all divided by 50. So FL is 550. So 500, divide that by 50, like, do it that way. You should have to use a calculator really. So it's 10. That would be the mechanical advantage of that system. So another thing we need to look at is that you'll find that if you had a flat tire and you're going to lift your car, you may find that you've got to wind your screw jack a lot more than the car goes up. Which means the distance the effort has to move, that's you winding your screw jack, is a lot more than the distance the load moves. Because the car goes up a little bit compared to how much movement you put in. For example, this here, to lift this load, we may have to, pull a lot more distance-wise just to lift this up. So we can lift a lot more, we just got to move a lot more. So in most cases, the distance the effort has to move is a lot more than the distance the load moves. When you've got a flat tire and you jack the car up with a jack, you turn the jack handle a lot more than the car lifts up. You may turn the handle round 10 times and the car only goes up a few millimeters. This is called velocity ratio. It is a ratio of how far the load moves. X just means distance and L means load, compared to how much the effort moves. E means effort and X just means distance. So all the velocity ratio is a ratio of how much the effort moves compared to the load. So if you've got to move, if you've got to turn your handle 10 times, which could equal 100 millimeters, your load may only go up 2 millimeters. So that's the ratio there. So that's one of the formula we'll be using. Velocity ratio is just the distance the effort moves over the distance the load moves. Obviously, you're going to be in meters. Right? It's a distance after all, so it's going to be in meters. Just a ratio. As with all moving things, machines have an efficiency. So, we have got friction and heat and loss of things, so there's an efficiency to everything. How much you put in compared to how much it comes out. Your car has an efficiency. Your washing machine has an efficiency. Even you have an efficiency, a percentage efficiency. You're not going to get 100% of what you put in. So the efficiency of a machine, or the efficiency of everything really, is the work done by the load, alright, divided by the work done by the effort, times by 100% normally. 100%. So efficiency is work done by the load, work done by the effort. So work done in, work done out. So we know that work done is force times distance. And so the force of the load times by the distance of the load is that like. And the force of the effort times by the distance of the effort is that, because work done is force times distance. This is work done. So efficiency is FL XL, FE times XE. So it's work done by the load over work done by the effort. That's one way of doing it. Or we could do force times distance of the load and force times distance of the effort. So it's another formula. Obviously it's a percentage, so it's like 50% efficient. So if you put in 100 and you get out 50, it's 50% efficient. You're never going to get 100% efficiency because we lose things. Heat, light, friction. So efficiency is force times distance, but we also know that FL over FE, FL over FE is MA, and XC over XL, XC over XL, is velocity ratio. Now, efficiency, efficiency we can do MA over VR, because that is over that and that is over that, but VR is E over L. So to put it in here, we'll just invert it. So efficiency can be worked out by mechanical advantage and velocity ratio. It can also be worked out by that, and it can also be worked out by that. All times by 100%, really. This is the symbol for efficiency. So efficiency is MA over VR. So if you see this weird symbol, that just means efficiency. So there's only a couple of formulas we need to know so far. It's going to be this. MA is FL over FE. Velocity ratio, XE over XL. And efficiency is work done by load, work done by effort, times by 100. Efficiency is FL XL over FE XE, F being force and X being distance, or efficiency is mechanical advantage over velocity ratio. So we'll do some examples as usual. So a pulley system has a velocity ratio of 5. The effort is 2 kilonewtons, so that's how much effort we're putting in. And this is the load. The load lifted is 5. So we need to lift a load of 5 kilonewtons, and we're putting in an effort of 2. Obviously the effort's going to be less because that's the idea of a machine. So with the gin, the velocity ratio is 5. We need to work out mechanical advantage and the efficiency of the system. Don't forget that weird symbol is efficiency. So mechanical advantage we know is FL, the force of the load, over the force of the effort. So FL over FE. So we've got FE there, look, and we've got FL. So FE is 2 and FL is 5. So MA is FL over FE, so it's 5 over 2. Because FL, the load is 5 kilonewtons, and the effort is 2 kilonewtons. So it's 5 kilonewtons over 2 kilonewtons. We can get rid of them if we wanted to. So 5 divided by 2, you should need a calculator, but we'll do it anyway. So the mechanical advantage of that is 2.5. Bit more to drink. So 2.5 is the mechanical advantage. And then we're going to look at the efficiency of the system. So efficiency we know is mechanical advantage over velocity ratio. We know MA, it's 2.5, and we know VR is 5. So we can do 2.5 divided by 5, 2.5 divided by 5. So it's a half. Right, don't forget percentage. So efficiency we'll do as a percentage, so we'll times that by 100. So this thing is 50% efficient, basically. So there's that one, lovely jubbly. Number 2, a screw jack has a velocity ratio of 8 and an efficiency of 30%. Calculate the effort needed to lift a load of 580 newtons. So there's my velocity ratio of 8. It's got an efficiency of 30%. Don't forget, we won't use the 30, we're going to use this. Because if you remember, it came out as 0.5 there, so we times it by 100 to get 50. So we'll put 0.3 in when we do it. Calculate the effort to lift a load of 580. So we know the velocity ratio is 8. We know the efficiency is 30 or 0.3. It's got to lift a load of 580, and we don't know the effort. So how much effort have we got to put in to lift 580? So here's a formula. We know that formula, and we know this formula. We know the efficiency. We know the velocity ratio. We don't know the mechanical advantage. So if we can work out the mechanical advantage, we can then find FE. Because once we know MA, we know FL is 580, we can rearrange this formula to find FE. So first of all, I'll work out MA. So use efficiency as MA over VR to find MA. And all I've done is brought this VR up. So there's my velocity ratio. So mechanical advantage is efficiency, it's not a H, it's just a weird symbol, right? Times by VR. So efficiency is 30%, which is 0.3, times by the velocity ratio, which is 8. Yep. So 0.3 times by 8 gives me 2.4 mechanical advantage. So now we know 2.4, we know this is 2.4, so now we know that number, we know FL, we don't know FE, so we'll rearrange this formula now to find FE. And all I'm going to do is I'm going to bring this up, so bring the FE up and bring the MA down. So FE is going to be the load over mechanical advantage. And we know FL is 580, and the effort, FL is 580, and the mechanical advantage is 2.4. So 580 divided by 2.4, this will give us the effort, 241.6 and a bit. So that there is how much. So to lift 580, we've got to put in 241. So that machine enables us to lift that much by that much. Nice and easy. Just using a couple of formulas. Just make sure when you're doing efficiencies, right? If that was 50%, you'd put in 0.5, right? Don't put in 30 because you get a funny number. So the law of the machine is not Terminator. So up until now we've ignored dead weight and friction. You should all know what friction is. So dead weight could be the weight of the machine in addition to the load. So you may have to lift the machine of a dead weight as well as the load. So friction due to pulleys, screw jacks, and friction caused by ropes, wires, etc. Energy is lost due to friction. So we need to put more energy in to overcome the friction. So we need to have a number for dead weight and friction. Normally it's just an extra force. We can work things out for friction, but in this case we'll just have a number to overcome the dead weight and friction. So the law of the machine includes both dead weight and friction. So here's another formula, which is called the law of the machine. So we know FE is the effort. This Fs is just a number for the dead weight and friction, and all friction. So you'll have a number, it'll just say 50 newtons is required to overcome the dead weight and friction. So that is just a number. Plus, all in brackets, FL is the load. That symbol there is efficiency, and VR is velocity ratio. So that's just another way of working things out using friction. So for example, calculate the effort required to lift a load of 500 newtons by a machine with an efficiency of 25% or 0.25 and a velocity ratio of 200. The dead weight in friction requires 30 newtons to overcome it. That just means this Fs is going to be 30. So we've got an example. So the effort required to lift a load. So the load's going to be 500. There's the load, 500. Efficiency is going to be 25% or 0.25. So that's 0.25. Velocity ratio of 200 goes in there. And to overcome dead weight and friction, we need 30. So Fs is going to be 30. So there's my formula. So Fs is 30. Fs is 30. The load is going to be 500. The efficiency is going to be 25%, which is 0.25. And the velocity ratio is 200 newtons. So to work out the effort required to lift that 500, whack that in. So I'll do this bit here first. Look, 500 divided by a quarter of that. Shouldn't really need a calculator, but I'll just do it anyway. Gives you that, plus the 30 gives you 40. Make sure you do all of this in the bracket. Then add that. So really, it should be like this really. 500 divided by 0.25 times by 200 plus, I'll get my calculator right, there we are, 40. So it's put a bracket around that really. It's all of this plus the 30. Don't do 30 plus 500 divided by that. That's the law of the machines. So it's just another way of working out stuff, including friction. So that's one you're going to need to sort of use. And screw jacks, I'll just describe screw jacks because they're quite common. Swing it in. A screw jack is used to lift a variety of things. Your car jack on your car is a screw jack, and all it is a screw basically. Actuators on planes, a lot of things are used by using a screw to push things, lift things, pull things down, move things up. So all it is a screw with a pitch on it, and it can lift and raise loads. So for example, this could be your screw jack here. So the load would be your car. So your car would be on top here. There's your car. That would be your car, funny looking car. And then this would be your screw jack, and this is your handle. So as you turn the handle in a circle, you turn the handle, lifts the load. So the load here is the load to be lifted. That could be a car, could be a plane, could be it's just the load. And XL, don't forget, is how far the load moves. So when I turn this handle, hopefully the load goes up. So this could be you turning the handle of your screw jack. As you turn the handle once, your car goes up a little bit. So the handle turns with effort. So this is where you put your effort in. So this handle would be turned with an effort. So you put a force there, and that FE lifts this load, which is FL. So there's your handle. Every time you turn the handle, which is going to be XE. Don't forget XE stands for the distance the effort moves. So every time you turn this handle in a circle, okay, if you put your hand on there and turn in a circle, so every time you go around once, this load goes up. The screw jack will have a pitch P, so we can say that every time we turn the handle in a circle, this thing goes up. The load will go up, distance P, which is that distance there. Somebody's on my phone, I'll just press pause. So as we turn this handle, so the load is raised a certain amount by turning the handle a number of times. Each time you turn the handle, the load goes up by the pitch of the screw. Don't forget, a screw has got little pitches on it. Not little pitches, right? You know, a little pitch. Distance that goes up every time you turn the screw. The handle moves in a circle, so the distance travelled by the effort, because we're turning this in a circle. So the distance is the diameter, right? Or the radius, that's how far we are away. So the distance moved is going to be the circumference of that circle. So the handle moves in a circle, so the distance travelled by the effort is the circumference of that circle. So we'll assume that we're putting our hands there. We know the length of this, which is the radius of the circle. So the distance moved by the effort is the circumference of that circle. So the circumference of a circle is pi d, or 2 pi r. So the length of this handle is going to be the radius. So the diameter, right, is going to be twice that, obviously. So you can either use pi d or 2 pi r. So one circumference, so the handle goes round once, 2 pi r distance. So once you move the handle round once, the effort goes circumference, causes the load to go up. So this goes round once, this load goes up, and it goes up, we'll assume, one pitch of that screw. Causes the load to move up by the pitch of the screw, which will be in millimeters. So don't forget, here's my screw, so there's the pitch. So every time I turn the handle, the load goes up by that amount. So the pitch of the screw is given in millimeters, but we must convert into meters. So this could be 8 mil, could be 2 mil, 3 mil, 4 mil, 5 mil. So every time we turn the handle, right, the load goes up by that much, or down by that much. So we can say that the distance moved by the effort is the circumference, which is 2 pi r. And the distance moved by the load is the pitch. Because every time you move, right, turn the handle, that's the effort, circumference, 2 pi r. Every time you turn that round once, this load here goes up or down by the pitch of this screw. So the distance moved will be the P, which will be in millimeters or meters. So after all of that, the velocity of the screw jack, the velocity ratio of a screw jack. So we know the velocity ratio is distance the effort moves over the distance the load moves. So the distance the effort moves over the distance the load moves. We know for screw jacks that the distance the effort moves is 2 pi r, which is the circumference, or pi d, it's up to you. And the distance the load moves is just the pitch of the screw. So therefore, XC is 2 pi r and XL is P for pitch. So the velocity ratio of a screw jack is 2 pi r over P. That's all you need to know, really. R will be the radius of the circle or the length of the handle. So whatever length this here is, this is the radius of our circle. That's the length we'll use. There, look. and P is just the pitch of the screw, which is whatever this here is, in meters. So another little formula for us, for screw jacks. So for example, a screw jack has a thread of pitch P, so that will be our P here. Look. It must raise a load of 600 newtons, that's the load, that's going to be FL, by turning a handle 500 mil long. So the handle is 500 mil long, this handle is 500 mil long, which means this R is going to be 500 or 0.5. The efficiency of the jack is 20% or 0.2 in our case, and the effort required to overcome the dead weight and friction is 20 newtons. That's our FS. Calculate the effort required. So here's the formula we'll use, because we can still use this formula. We don't know what FE is, because we're trying to find it. We know what FS is, because it's 20. We know FL is the load it's given to us, which is 600. The efficiency is going to be 20%, which is 0.2, don't forget. We don't know the velocity ratio. So we know FS, we know FL, we know efficiency, and we don't know VR, and we don't know FE. So before we find FE, we've got to find VR. It's a screw jack, so we can use this formula here from before, here. So velocity ratio is 2 times pi times the radius, which is the handle length really, which is going to be 500 or 0.5, all over the pitch of the screw, which is 5 millimeters, which is going to be 5 times 10 to the minus 3 meters. Don't forget. So 2 times pi times r, so the radius is going to be 500 mil, which is 0.5, and the pitch is going to be 5 mil, which is 5 times 10 to the minus 3. That'll give us the velocity ratio, so let's do it up here then. 2 times shift pi times by the radius, which is going to be 0.5, all divided by, what's going on here now? Let's go up, let's go across, start again. 2 times shift pi times by 0.5, the length of the handle. Come down here and we need to do 5 times 10 to the minus 3. Close that, come there, pass equals. 200 pi is the answer, but we'll put it in like that. So 628, that's our velocity ratio. So now we know this. That's going to be 628. So now we know all the numbers, so we can just put them into the formula, which will give us the effort. So there's the formula. Don't forget we've got to do all of this first in a bracket. So 600, which is FL, which is over here. Divide that by the efficiency, so it's 20%, so use 0.2. Times that by velocity ratio, which is going to be 6 to 8.32. Put a bracket around all of that, look, because it needs a bracket around all of this. Let me do it, come on. And let's go over there. Let's see if we can go, what we're doing there. Let's go there. Come on. There's all of that. You can do it quickly if you want to. Plus the 20 gives me 24.7. So that's the effort needed. How much effort you need to put in, perhaps, to lift your car with a screw jack with parameters like that. So the effort needed to lift a load of 600 is 24.7, which is not bad really. Screw jack. So number 2. I think I've only given you 2. Have I given you 2? I've given you 3. Hey. So number 2, screw jack as a thread. So here's the pitch, 6 mil, and a handle. So there's the handle length, which is going to be R. There's the load, 2000, efficiency is 30% or 0.3. The effort required to overcome friction and dead weight is 15, so calculate the effort. So again, we need to find the effort, which is Fe. Again, we know what Fs is. Fs is going to be 15. The load is going to be 2000. The efficiency is going to be 30%, which is 0.3. And again, we don't know velocity ratio, but we do know for screw jack, velocity ratio is going to be that, 2 pi r over p. So we know 2 times pi, the radius is the length of our handle, which is handle 250 mil, so that's going to be 0.25, and the pitch is 6 mil, 6 times 10 to the minus 3. That'll give us the velocity ratio. So 2 times shift pi equals that, times by 0.25 equals that. Divide this by 6 times 10 to the minus 3 equals 261.8. So that's the velocity ratio. So thank you very much. Now we can put that number in here because that's the velocity ratio. So Fs is 15 because we got it from before. FL is 2000. The efficiency is 0.3 and the velocity ratio is that. So put it in this formula. That will give you the effort. Make sure you put a bracket around that and a bracket around that. So 2000 divided by 0.3 times by 261.8. Close that. Plus the 15 gives me 40.5. So that is the effort required to lift that load of 2000. So same as before, really. Next one, number 3. Now this one I'm done a little different. We've got to find FL. So I'm going to rearrange this formula now. Still a screw jack. So still got a pitch of 7 mil, lever radius of 300. So that's our velocity ratio sorted. Calculate the load. So it's not effort, it's the load. Now we need to work out how much load this thing can lift. So we've got an effort of 500. How much load can we lift with that effort of 500? The efficiency of the jack is 25%, which is going to be 0.25. Assume the effort required to overcome friction and dead weight is 40. So with this, we know Fe, we know Fs. Alright, so slightly different from before. We know the effort, we know friction. We don't know the load in this case, so we need to find that. We know the efficiency and we know VR because we can work it out. So we know everything apart from FL. We need to rearrange for FL. First of all, I'll work out VR first. We'll do VR first down here because we don't know what it is really. We know everything else. That's your effort, that's your efficiency, that's your friction. So VR is 2 pi r over p. R will be the radius, which is 300 or 0.3, and the pitch is 7 mil. So 2 times 0.3 all over the pitch. So there's the pitch and there's the handle. So put that on your calculator. 2 times shift pi times by 0.3 equals that, divided by 7 times 10 to the minus 3. Gives me, come on, 269. That's my velocity ratio. Thank you very much. So now I know everything apart from FL. Sound good about FL? Don't know FL. So I need to rearrange this formula to find FL. So the first thing I'm going to do is I'm going to bring Fs across. It's a positive number there, so I'm going to make it Fe, take away Fs. So the effort, take away the friction and the dead weight. equals all of this. I've just moved the fs across, so it gives me that. Now all this down here is divided by, so I'm going to bring it up, I'm going to multiply it all in one go. So I would keep brackets around this just to keep everything in order. So there's that bit there. I've brought this up, the efficiency and the velocity ratio up, brought it up to there. That then equals FL. So that there is how to find the load that we can lift. So FE is the effort, which is 500. FS is the friction, which is 40. The efficiency is going to be 0.25. And the velocity ratio is 269.3. So put that in your calculator, keep your brackets in the right place. 500, take away 40, don't really need a calculator for that, times by the efficiency, which is 0.25, 25%, so 0.25 times by 269.3. Close the brackets. 306,969.5 newtons, that's correct. Or if you want to, press NG, 30.97 or kilonewtons. So that's how much of a load I can lift with that effort. So if I put an effort of 500 in, I can lift a load of 30 kilonewtons. So what you can do is, to check this number, because you also check that everything's correct, one way you simply could do it is put it back into the formula. So I know that I worked out 30.97 kilonewtons. So I'm going to put it back in the formula. I'm going to put it back in this formula and pretend I don't know what the effort is. So I put all the numbers I've calculated in here. I know that number. If I put the number I've worked out for FL, in there, and the number for VR in there, and the efficiency, which I'm given, if I put them all in that formula and I get a number for FE, which is 500, I know I'm correct, really. So that's what I've done there, look. So I'm pretending I don't know what the effort is. We know it's 500, but so FS is 40. My load is the number I've just worked out. That's my velocity ratio, and that is my efficiency. So if I put that back in and I get 500, which I do, then you can be happy that you're roughly right. There's one way of just checking numbers. So I'll just do it. That divided by 0.25 times by 269.3 plus the 40 gives me that 500. So I'm quite happy that that is correct. So that is law of the machine's velocity ratio, efficiencies, screw jacks, etc. There will be questions in your assignment on this, and I'll put some questions for you to do. But for now, practice, 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 over and